So although we're going to talk about alcohols in this, we're actually going to talk about lots of different functional groups. But before we get into the more interesting bit, we obviously need to look at what makes an alcohol, and of course it is this OH group. So it's OH which makes it an alcohol, and how do we name them? Well, this guy's got one carbon, so we start with it being methanol. So it's the ol which tells me it's an alcohol. This one is the one that you will be familiar with in terms of it being a beverage. That is, of course, ethanol. This one will kill you. This one will kill you slowly, yeah. Now, when we get to 3 carbons, obviously things get slightly more interesting. This guy, what would he be called? Propan, yep, but do I need to put a number? Propan 1-ol, yeah, cool. Propan 1-ol, because if I swap it around and put an OH there and that becomes an H, that is then propan 2-ol. So as soon as you get to 3 carbons, you need to start putting your number here where it is. Again, I'm going to be a real pain as well. When you're drawing, you've got to be really careful. The bond goes to the O. So don't get sloppy with how your bonds go. If you did this, so say you did that, you could lose a mark because you're showing the bond going to the H. So just be really careful about how the bonds link up with anything like that. When we start looking at the properties of the alcohol, most of these 3 will all mix with water. They're miscible with water because they're liquids. So these are quite happy in water. When we get to 4 carbons, they become immiscible with water. So by that I mean if you had a little test tube with them in, you'd get 2 layers, one for the alcohol and one with the water. They're not going to mix up. But these 3 will. Why, first of all, will they in theory mix with water? What will pull them into the water? Yeah, the OH, because we can have hydrogen bonding between the OH group on the alcohol and water. What's stopping this guy going in? What are the forces between CH groups with this bit? This bit is what's going to be the type of interaction in terms of intermolecular. Yeah, these are going to be van der Waals here. This is going to be OH bonding. Will water like van der Waals getting in the way? No. So because this bit, have you heard of the term hydrophobic? Yeah. This bit's going to be hydrophobic. Doesn't like that bit is hydrophilic. But eventually, this bit gets so long that although this will mix, this pulls it into the water, this stops it. And so when you get to 4 carbons, it ain't going to go in. In terms of hydrogen bonding, they sometimes ask you to draw between water. For your hydrogen bonding, you've got to be really specific about that. First of all, draw a water molecule. That's delta plus, delta minus, delta plus. And then if I'm going to do it with methanol, I then put my H bond there, and then that is going to go to a hydrogen O, and then that's going to be a CH3 group there. That's delta plus. That would be delta minus there, and that there is your hydrogen bond. So sometimes they'll ask you to draw between water and methanol, which shows it coming in. So you may want to just knock that down where it says hydrogen bonding between alcohols and water. Pot that one. Hydrogen bonding between 2 alcohols, you can pretty much do the same.
Is that hydrogen bond happen with all alcohols?
Yeah, absolutely, yeah. So if I do it with methanol, like so. Oh, no, I've got to give myself a bit more space there. So if I do CH3, H, like so, delta plus, delta minus, and so on that. So that's the hydrogen bonding between 2 methanol molecules. Just make sure you show your lone pair That there is your hydrogen bond. Hydrogen's always delta positive and oxygen's delta negative, like so. So the well-established way of making ethanol only is, of course, fermentation. Through that, you take glucose, C6H12O6, and you pop in some yeast, and this has to be dissolved in water. So get some glucose, dissolved in water, put up some yeast, about 35 degrees C, and you make ethanol, C2H5OH, which is dissolved in water plus carbon dioxide gas and so on. So that's the established way. The problem is you may be aware is once you get a certain concentration of alcohol, the yeast die. So you can't keep going. I think you can only get to about 20% or so, and then the poor yeast will no longer function. So it means you've got ethanol dissolved in, mixed with water. So you've got to distill all the ethanol off, which is really expensive to do. You've got to maintain it at 35. So this works really well for warm countries like Brazil, where they can just, the ambient temperature will keep it going. And then you can distill the ethanol off. The other thing is you must keep it in the absence of oxygen. So you can't have any oxygen around through this at all. Otherwise, this will be oxidized to ethanoic acid. So that's one way of doing it. Works quite well, and that's when often you use ethanol as a biofuel, because you can grow the sugar cane quite easily if you're in a warm country. Pop the sugar, make the ethanol, Bob's your uncle, all done. The way that you would normally make it though is through reacting it with ethene, which we did in our last topic, and you react it with steam to produce ethanol, like so. So it's got to be steam, so it's got to be above 100, and you need a phosphoric acid catalyst for that. So you need to be able to compare the two processes which you would want to use. So this is good because it's continuous. You keep putting the ethene in with steam and you make ethanol. So generally you would use that if you want to have really pure ethanol in industrial processes. And where am I going to get this from? Crude oil again. So again, it's not good because I'm using up crude oil. Any questions about those two processes? You just got to learn those two. If you think when you're growing your sugar cane, you're going through photosynthesis. So you've got 6 carbon dioxide plus your water making your glucose, which is all fine and dandy. You then take your glucose and you make ethanol, and that produces a bit of CO2. You then take your ethanol and burn it, and that makes 4 CO2. So I use 6 CO2 up here in making my glucose. I then take my glucose, and to produce ethanol, I make 2 CO2, and then when I burn it, 4 CO2. So in theory, it's neutral in terms of carbon dioxide. Yep, I use 6 CO2 here and I make 6 CO2 here. Do you think it is, in theory, completely carbon neutral in that? What haven't I built in?
Transport.
Yeah, I haven't thought about, is this all going to happen in one side? Will this be 100% efficient in terms of that as well? I also haven't built in the fact that I've got to distill this off in some way as well, which costs energy. So there's lots of things you have to think about this. So this is often called in the news, this is completely carbon neutral, this will solve all our problems, but actually it's not completely carbon neutral. The other issue, of course, is if I'm growing sugarcane here, I've got to grow that in some way using fields. So those fields are no longer being used to produce crops. So if you do geography, this will be really bog standard for you. So if I'm not using that for food, that's going to make the prices of food go up and so on. So the other issue is where if this is grown in Brazil, what am I destroying?
Sugar forest.
Sorry? Rainforest, yeah. So I'm destroying the rainforest to grow the sugar cane for that, which isn't good as well. So there's lots of problems.